everyone, and thanks for tuning in to BEaTS Research Radio, a podcast and YouTube channel that aims to disseminate science and research to the community. My name is Nicole Chu, and I'll be your host on today's episode. Today, we are honored to be joined by Dr. Sophie Lerouge. Dr. Lerouge is a full professor in the Department of Mechanical Engineering at École de technologie supérieure and Adjunct Professor at the University of Montreal. She is also a principal scientist at the CHUM Research Centre in Montreal, Quebec, and was the Canada Research Chair on endovascular implants and biomaterials from 2008 to 2018. Dr. Lerouge's research focuses on the design and evaluation of novel biomaterials, surface coatings, and hydrogels for applications in vascular diseases, cell therapy, and tissue engineering. Thank you so much for joining us today, Dr. Lerouge.
Hello, Nicole. Nice meeting you.
We're so happy to have you on our channel. So to begin our conversation, can you please just give us a general overview of the main focus of your team's present research?
Yeah, well, the main focus of my team is designing and evaluating injectable biomaterial scaffold to improve minimally invasive treatment. For example, as I said, we can discuss that later, but endovascular occlusion of blood vessels, cell therapy for cancer treatment or ischemic diseases, and also for bioprinting. Our approach is, in fact, to answer to real clinical needs, and therefore we are working in close collaboration with clinicians and industrial as well, and here at the CHUM. And our multidisciplinary approach is what is interesting and maybe quite unique is that we have really all the infrastructure to go from the bench to the bedside, including animal testing, and this also collaboration with clinician and industrial.
Oh, I see. So you mentioned like a large focus of your team is investigating and evaluating these novel biomaterials. And in particular, a big focus is with hydrogels. So I'd like to ask, how can these injectable hydrogels be used in blood vessel embolization and cell therapy?
So in fact, we have created smart hydrogel that are liquid at room temperature, but that gel in situ at the body temperature. So they can be injectable through small catheters or small needles, and they rapidly form a cohesive gel, which can after that withstand the stresses and so on. And this hydrogel can contain either drugs, bioactive agent, or even cells for the cell therapy or bioprinting application. So the main achievement, we say, has been really the design of a hydrogel with better cell compatibility and much stronger mechanical properties than the previous thermosensitive hydrogels. We were not the first to develop thermosensitive hydrogel or in situ gelling hydrogels, but we really improved the cytocompatibility and the mechanical properties of this. And now we are using this, one of the formulations, we have different formulation, of course, but one of the formulation allows to occlude undesirable blood flow. Of course, we all know about opening arteries using stents, but in some case also the blood flow are undesirable and we need to occlude them. So for example, some veins or arterious venous malformation and so on. So this gel can be injected through a catheter and then it blocked the flow and it prevents the undesirable blood flow. And so we are doing that in collaboration with an international leader in endovascular treatment company. And another formulation has shown very promising results with cells. And so we can use them either as a macrovolumic gel, so a gel that we can inject, or it's in the form of small microbeads that contain the cells and that are injected in the body. And they can either be released or just release their angiogenic factors and so on. So we use it, for example, with T lymphocytes for the cancer treatment, so these T lymphocytes are delivered and grow in the scaffold, and they are then going to to fight the cancer. So it's locally injected through close to the cancer, and they can deliver the T cells, or we can put, for example, mesenchymal stem cells to regenerate tissue to help for ischemic disease. So these T cells will secrete their pro-angiogenic and immunomodulatory factors and they so that in the scaffold themselves. That's why those scaffolds are very useful, because otherwise the cells would rapidly die or be going somewhere else than in the target tissue.
Oh, I see. That's really interesting to see how your team is modifying these hydrogels and the wide range of applications for cancer research and also blood vessel embolization. So, speaking more on specifics of your research, one of your recent publications actually investigated fresh bioprinting of biodegradable chitosan thermosensitive hydrogels, so sort of a mouthful. But compared with other types of these biomaterials, what makes these biodegradable chitosan hydrogels so unique?
First, something that should be said that there is like hundreds of hydrogels and polymeric scaffold for drug delivery. And I think, but when it's a question of cells, it's much more difficult, because the cells can be harmed by many factors. So we need to avoid any shock to the cells. So the chitosan hydrogels that we have developed are unique in this sense, because they allow in situ gelling, easy mixing with the cells when they are in liquid. They have like a physiological pH. They are biodegradable. There is no cross-linker or any modification. They are easy to prepare, and all this is what the industrial want. They like nice work, but they like simple stuff that can be easily transferred to the clinics. So I think this is one of the main advantage of these hydrogels. So excellent cell biocompatibility, good mechanical properties, tunable gelation rate, and easy preparation and mixing and everything.
Oh my!
So this is for hydrogel in general. For this hydrogel, for bioprinting application, we can then discuss a bit later. But I think this is why they are unique for also for bioprinting.
No, yeah, thank you for sharing. And as you mentioned, the bioprinting part, for those who may not know, do you mind explaining what the fresh bioprinting method entails?
Yeah, so first, let me introduce bioprinting by itself. So bioprinting is a kind of 3D printing technique, but the difference is that we don't use polymers or metallic materials. We use scaffold and in general hydrogels containing cells. So the idea is to create 3D structures containing cells for example, as drug screening, or later even for implantation, and create new organs and tissues. So the fresh bioprinting is a different approach, which allows to use a support bath, because one of the main difficulties is when you use a hydrogel, they are not so hard or cohesive or mechanically strong, so they tend to collapse under the next layer. So if you use like materials such as collagen or chitosan, they tend not to make very nice resolution structures, because they collapse under the. So using a support bath allow them to create really nice 3D structures, and then we can remove the bath and we have the 3D complex structures done. So this is what we can use within the principle of the fresh bioprinting technique.
Oh, I see. So we've gone through, the why these hydrogels are unique and the principle behind fresh bioprinting. So what problem or limitation did this fresh bioprinting method allow researchers to overcome in regards to the fabrication of these 3D structures with these chitosan hydrogels?
Yeah. Well, in a way, I almost gave you already the answer, but as I said, these chitosan hydrogels are very soft and tend to collapse. So I think the fresh bioprinting technique, what we developed is a new support bath, a warm support bath that allows to take advantage of the thermosensitive properties of the chitosan hydrogel. So it's a support bath that allows better resolution, but also that enables better gelation, because it's warm, it's at 37 degrees. So the gel can really gel faster and create more cohesive structures. Otherwise, we can see a huge difference when we without the fresh approach, and with the fresh approach in terms of resolution and mechanical properties of the 3D structure that we are creating using that. So it's make a big difference, and it will allow for other application as well. We can use chitosan, but mixed with other hydrogels such as collagen, for example, to create other structures.
Oh, I see. Thank you so much for explaining that for our audience. And thank you, Dr. Lerouge, for coming on our channel to share your research work.
Well, it was a pleasure. Thank you. Have a nice day.
Yeah, and thank you to all BEaTS Research Radio listeners for your time. Don't forget to like and subscribe to our YouTube, Twitter, and Instagram channels at BEaTS Research. BEaTS Research Radio is supported by the University of Ottawa Heart Institute, BEaTS Research Laboratory, and the University of Ottawa. We hope to see you all next week.